Okay, let's talk about damped-free vibrations. Okay, so like in the previous video, we talked about undamped free vibration motion, right? Which means there was no damping term. But for this one, we're gonna add a little bit more. Okay, so we're gonna have like damping term, which is gamma u prime. We're talking about this term, right? But good thing is it is still homogeneous second order linear differential equation with constant coefficient, right? And keep that in mind, gamma is also positive value. Then also we can use the characteristic equation for this one because that is still second order linear, right? Then for this one, it is exactly like quadratic equation, and we can solve this equation by the quadratic formula, right? Which is minus b plus a minus square root b squared minus 4ac over 2a, right? And also like here, and we would like to write minus gamma over 2m and square root part separately, because like depend on this square root part, and we're gonna have like different situation. First one, whenever gamma square minus 4mk, which is under the root function, is positive, then that case, positive case, okay, then you're going to have the exponential function form of the solution, right? But whenever like your gamma square minus 4mk is equal to 0, then it's duplicate case that we covered like in the previous sections. And then third case, when your gamma square minus 4km is less than 0, which is imaginary number, okay? We're going to take out all these three cases, okay? But basically, damped motion means there's damping term, which means like your oscillation is not going forever, but it is slowed down and it will be stopped. Okay, and that is basic idea about this problem. Okay, so we're gonna start from under damped motion. Okay, there we go. Under damped motion, and this is the case. Your gamma square minus 4 mk less than 0, which means you're going to have negative value under the square root. Okay, so this means your gamma square is less than 4 mk. Okay, if your, as I told you, like if your gamma square is less than 4 mk, you're going to have like complex number as your solution, right? So okay, there we go. Let me rewrite your R. Your R was minus gamma plus a minus and square root of gamma square minus 4 mk over 2m, right? And also we rewrite this one with a separate form, which is minus gamma over 2m and plus a minus and square root of gamma square minus 4 mk over 2m, right? As you remember, like this part will be the exponential function. Sorry. Okay, and minus gamma over 2m will be the exponent part, and then this part will be part of the trigger function, right? Sine and cosine part, right? That's what I'm gonna do. Okay, so like for my convenience, let me say this is lambda, which is exponent, and let's say this is mu, okay, which will be the sine and cosine function, okay? And then I can write R as lambda plus and minus. Give me 1 second, not mu, but let me define like this one. This part is the square root of 4 mk minus gamma square and I over 2m. Then I will define this part as a mu, okay? Then I can write my R is equal to lambda plus and minus mu I, okay? And with this R, which is solution of characteristic equation, we can write the general solution, okay? There we go. Therefore, the general solution is, let's say ut is equal to coefficient a times e to the lambda t times cosine ut plus another coefficient b times e to the lambda t sine mu t, right? Okay. Then as we did this before, we can combine as one single cosine function, okay? And okay, let me skip that part, but we can write this one directly, okay? It will be r times e to the lambda t and cosine of mu t minus delta, where your r is equal to square root of a squared plus b squared, and tangent delta is equal to b over a, or your delta is equal to tangent inverse of b over a, right? That's what I did, right? So, okay, we're almost there, okay? So like, look at that. Your general solution is like a form of the cosine function, which means it's oscillate, right? Since my lambda is less than 0. Do you understand why? Okay, let me come back to like definition of lambda. Lambda was defined by minus gamma over 2m, right? Let me rewrite here, okay? Minus gamma over 2m. As you remember, gamma is positive and m is also positive, right? That's why your lambda is negative value, okay? Then what happened? Look at that. E to the lambda t goes to 0 as your t is increasing. Doesn't make sense, okay? Then like, as you know, like cosine has like, just like between minus and 1, and your ut goes to 0. Is it okay? Therefore, your ut goes to 0 as t goes to infinity. Does it make sense? Okay. So, well, like, let me give you the graph of this solutions curve, okay? And it looks like this, okay? So like, well, if I like, just make the line for the like tops and lows, looks like this way, okay? Like when time is increasing, your graph will be like oscillation is just getting smaller, 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 and finally converts to 0, which is equilibrium position, okay? So, well, like this one, like we can talk about the like, frequency and period, okay? But it is not exactly like frequency and period, but it's kind of like frequency and period, right? That's why we're going to use quasi-frequency and quasi-period instead of like a regular frequency and period, okay? There we go. So the solution oscillates with quasi-frequency, which is mu, and quasi-period, which is, let me like, TD, which is 2 pi over mu, right?